If you're formulating a generic pharmaceutical liquid or semi-solid, then you'll often need to submit some evidence of what we call structural equivalence of your product to the reference listed drug or the originator's product to the regulatory bodies. A range of rheological properties are often requested to gain a comprehensive comparison of the two formulations. We provide this as a service for our customers. But if you want to do this yourself, or you just want to get a better understanding of the properties involved, then here's a super quick guide. So what are the authorities typically asking for? Well, here's an example from the US FDA's draft guidance on acyclovir, common generic topical. And here's an example from the European Medical Agency, the EMA, draft guidelines on quality and equivalence of topical products. So let's pull out some of the key requirements in these. A complete flow curve of shear stress or viscosity versus shear rate. Shear stress is a measure of how hard you push a material. Shear rate is a measure of how fast it flows. So viscosity, therefore, is just the ratio of how hard you push to how fast it flows, the ratio of stress to shear rate. So suspensions, emulsions and gels all exhibit non-Newtonian shear thinning behavior. So that means their viscosity is dependent upon shear rate and the viscosity decreases at higher shear rates. However, if you measure the viscosity across a wide range of shear rate, you're going to get a plot that looks something like this. You can see here that the non-Newtonian shear thinning only occupies the middle shear rate region, but Newtonian behavior is seen as low shear and high shear plateaus. The viscosities attained at these plateaus are known respectively as the zero shear viscosity and the infinite shear viscosity. Zero shear viscosity is particularly interesting as it can give you an idea of the mobility of suspended solids or emulsified droplets when in a close to at-rest condition. So when the FDA asks for a complete flow curve until low or high shear plateaus are identified, this is what they mean. And I'm pretty certain that this is also what the EMA refer to when they quote linear portions of the curves. So the bit in the middle, the shear thinning region, is usually a straight line, so this could be fitted to a power law model. But if you want to model the whole curve, then you can use a modification of the power law model, such as the cross or the Carreau model, and then that will quantify the zero shear and the infinite shear viscosity values as well. Incidentally, notice that we're using logged axes here. This is because on the shear rate axis, a lot of interesting stuff occurs at the low end that we want to emphasize. And on the y-axis, well, the changes in viscosity could be enormous, and we need to fit it all in to make sense of it all. If this was plotted on a linear scaling, it's going to look like this, which is next to useless. Okay, so next is yield stress. Yield stress could be thought of as the strength of the soft, solid structure that is created in your product as a result of a mass of interactions, droplet interactions, particle interactions, surfactants, polymers, that kind of thing. Yield stress is a key contributor to application properties, sensory properties, delivery from a container. Therefore, it's really important when it comes to topical products, anything that goes on the skin. Yield stress can be measured in a number of different ways, one of which is to use oscillatory stress sweeps. Oscillatory testing comprises a really cool set of techniques where you nudge your sample structure very gently and watch it bounce back. In an oscillatory stress sweep, phase angle, effectively a measure of the presence of structure, changes as stress is increased. An increase in phase angle indicates the disruption of structure as the yield proceeds. At that point, we've identified the yield stress of the sample. So next in the guidelines we see linear viscoelastic response, storage modulus and loss modulus as a function of frequency. When we oscillate at very small stresses, we operate in what we call the linear viscoelastic region for the material. The storage modulus and the loss modulus are just the elastic and the viscous, so the solid-like and the liquid-like contributions to the overall rigidity of the sample structure. So if you want a simple but very unscientific explanation of storage and loss modulus, then you should take a look at my video, Storage and Loss Modulus for Beginners. So the regulatory bodies request storage and loss modulus versus frequency. In the test, the sample is oscillated at a range of frequencies, effectively imposing a range of deformation timescales on the sample. The reason they do this is that by assessing the relative relationship between the moduli across the range of frequencies, it's possible to identify similarities or otherwise that are reflected in microstructure. A typical pharmaceutical cream, for example, will usually exhibit what we call an elastic dominant response, with G', the storage modulus, being higher than G', the loss modulus, across that range of frequencies. So if that's not the case for the generic version of the formulation, then that suggests a lack of structural equivalence. Okay, so finally, creep testing. Creep testing is far less popular and common than the viscosity profiling or the oscillatory testing methods. Creep testing entails applying a small stress to the sample, maintaining that stress over a period of time, and monitoring the strain, so the amount of deformation, as the experiment proceeds. So the sample has undergone an initial highly elastic deformation, but eventually the deformation rate slows to a steady state viscous flow and the plot straightens. The slope in the steady state region gives us the shear rate. By dividing the applied stress by this shear rate, we obtain a viscosity, and because this viscosity was attained at very low stresses, well into the linear viscoelastic region, the viscosity is indicative of the viscosity in a close to at rest condition. Now I suspect that this is the only information that the authorities take into account from a creep test, but if anybody knows otherwise, please let me know. Okay, so we've covered some of the information here that's required by the regulatory bodies to assess the equivalence of a generic product to a reference listed drug. Actually gathering the data on your samples is not often the easiest of tasks, and getting reliable, repeatable data that's free from artifacts can be a challenge. If you need some help in that department, then contact us. Come through the website at rheologylab.com or drop us an email at lab@rheologylab.com, and we'd love to help you. Please hit the like button if this is working for you. Subscribe if you want to see more videos, and I look forward to seeing you at the next one.